Okay, hi everyone. Today we're looking at exercise 13E and a new topic called logarithms. Okay, so now what we're going to look at is the logarithmic form compared to index form. Firstly, we would recognize this one as being in index form because we've got 2 raised to a power and that's equal to 8. In this expression we would say that the index is equal to 3 and the base is equal to 2. They're two fairly noteworthy things to remember. Now, the same expression can actually be written in what we call logarithmic form. When we write it in logarithmic form, the base, which is there, gets written down the bottom. There is a rule that says that a logarithm is an index. Since we know that the index was equal to 3, that means the logarithm, the index that is equal to 3. This means that 3 can only go there. So that means that the 8 must go in the other position, which is here. There's just a few little things to help that. 8 goes there, the base goes there, and the 3 goes there. Notice also that when we write out logarithm base 2, normally we'd write the 2 below the line, log 2, 8. So if you imagine a line being drawn there, the 2 actually is written below the line, equals 3. So what we can say is that if something is in the form a to the x equals a, this is in index form. We can convert this into logarithmic form and they represent equivalent statements. Let's have a look and see what happened with this one. The index was equal to x. So the index is the logarithm is equal to x. The base was a. Where did it go? Where the base goes. And where does the y go? There's only one other place, and that's right there, isn't it? And just a reminder that the logarithmic form makes the index the subject of interest. Other words, the logarithm is an index. So now what we're going to do is to look and see how we can apply our newfound knowledge. Here we see that a to the x equals y can be written in logarithmic form. Log base a of y is equal to x. Remembering the index was the logarithm. Let's have a look at the first example. 3 to the power 2 is equal to 9. We see the base is equal to 3, the index is equal to 2, so another way of writing this is log base 3 of 9 is equal to 2. In this one, we see that the index is equal to 4, the base is equal to 10, so index is equal to 4, base is equal to 10, and so it goes. In this one, let's rub that out. A to the 0 is equal to 1, so writing this in logarithmic form, log base a of 1 is equal to 0. That turns out to be an interesting result. So as it turns out, log to the base anything of 1 is always going to be equal to 0. We'll need to remember that for later. A to the 1 is equal to a. Well, we kind of knew that anyway, didn't we? But if we're putting this in terms of logarithmic form, we get another very important result. And that is, if these two turn out to be the same, the answer is always equal to 1. For example, log base 2 is equal to 1. Log base 3 of 3 is equal to 1. So if these two numbers are ever the same, the logarithm or the index must have been equal to 1. Now, this says, without the aid of a calculator, evaluate the following. Let's look at how this works. We start by saying let log base 2 of 32 equal x. If we write this in index form, we can use our SOC rule. So we can say 2 to the power of x is equal to 32. We can see, I hope, that 32 is equal to 2 to the power 5. Once you've got the same bases, we can say, therefore, x must equal 5. Let's do the other one the same way. Log base 3, 81, let's make that equal to x. If we now write this in index form, 3 to the power x equals 81. 81 is equal to 3 to the power 4. This means that x is equal to 4. Now, because x was equal to log 381, this means that log 381 is equal to 4. Now, we've already seen a couple of the rules of logarithms already, but let's have a look and see officially what rule numbers are which logarithm laws. So we already know that a to the x equals m is in index form, can be written as log base a of m is equal to x. We already know that a to the y equals n would imply that log base a of n is equal to y. We're going to need those for our first rule. In our first rule, we let m times n equal a to the x times a to the y. Why is that? Well, that was m, that was n, so m times n must be a to the x times a to the y. Can't complain about that. But what we can do is we can add the two indices together. That gives us a to the x plus y equals m times n. Then we can rewrite this in logarithmic form. Remember, we now know the index was equal to x plus y, so that goes here. The base was equal to a, so the equivalent expression is log a of mn is equal to x plus y. Now, let's keep going. What that means is, since x in the first part was equal to log am, x plus y can be written as log am plus log an. We have discovered rule 1, and that is log a of mn is equal to log am plus log an. Let's keep going. Here's the example. What we notice is we've got the same bases there and there. If we've got the same bases there and there, it's like this expression here. So what that means is we can combine these two together. What's our law? It says if we've got log am plus log an, it's like having log a 200, that's log 10 200, plus log 10 5. All we do is multiply these two together. So it gives us log 10 200 times 5. Let's rub all that rubbish out and look at the neat version. And so yes, log 10 200 times 5, and that's equal to log base 10 of 1000. Now that's equal to 3. Why is that? Well, we saw that before, didn't we? But for now, let's just trust me, that's equal to 3. I will show you again later on exactly why that's true. Okay, so let's look at rule 2. Rule 2, we've got our same suspects here. We've got the m and the n, but this time we're dividing, so we're saying m divided by n. So m divided by n must equal a to the x divided by a to the y. Okay, that's a reasonable start, isn't it? Now, we can rewrite this one as being a to the x minus y, because when we're dividing by a to the y, we just subtract the indices. So another way of writing this is a to the x minus y is m over n. Now we can rewrite this in indicial form, in logarithmic form. So the base is a, it goes there. The index is x minus y, it goes there. M over n has no other place to go except there. And what we've done is we've discovered another rule. And here's our second rule. So when you've got log am and you've got a minus sign between, you actually divide m by n. And there it is. Here's an example. So if we've got log 10 32 minus log 2 8, what we notice is same bases. Where you've got the same bases and a minus, we divide 32 by 8, and that's going to give us log 2 4. Turns out that's equal to 2. So now we're going to look at rule 3. Okay, here's what we know. Log a m over n is equal to log a m minus log a n. But what about if m was equal to 1? If m was equal to 1, that means we'd have log a 1 over n is equal to log a 1 minus log a n. Do you remember from a previous slide that whenever you've got log a 1, that's equal to 0? So we can say that log a 1 over n is equal to negative log a n. If that's the case, we've discovered our third rule. And there it is, log a 1 over n is equal to negative log a n. There it is up there. And now let's look at rule 4. So rule 4, we start with a to the x equals m. And now what's happened? We've raised both of these to the power of p. I wonder why we've done that. So if that's the case, remember we can multiply the x and the p together. And now we can put this into index form. So we can say log, the base was a, so we're taking it from there. The index was equal to xp, so that goes there, and this time the mp comes down here. So, does that help us or hinder us? I'm glad you asked. Let's find out. What we notice is that p can be written at the front. The x, remember, where was the x? That was equal to log am. So we've got p log am. This is a so-called plug law. So let's have a look and see what it says. If we've got an index here, it can actually be brought down to the front and make that p log am. Aha! We now have our fourth rule. Alright, we're looking good, aren't we? Let's look at an example of that. In this one, we notice the 3 is outside the log. If we wanted to bring it inside, it means it's going to become the power. So it becomes log base 3, 4 to the power 3. In turn, 4 to the power 3 is equal to 64, and that would be our answer. Okay, let's have a quick look at a summary. Okay, we know these. So there's our rules. Now, this is one that we didn't write down as our official rules, but we did see them before. If you've got a to the 0 equals 1, that means log a1 is equal to 0. If you've got a to the 1 equals a, that gives us log a is equal to 1. Now, I would say to you, it's a very good idea to be memorizing those rules there. Perhaps the derivation doesn't make that much difference, but if you do remember these rules here, it's going to make life a lot easier for you. I can promise you that. Now, a little caveat down the bottom, that provides that a is not equal to 1 or a is not equal to 0. So in this example, it looks quite complicated, and it's a fairly standard exam type of question where you've got to simplify the expression there. First thing we actually look for is to see if all the bases are the same. They are, so that means we're going to be able to use our log laws. Well, look at the 2 there, it's outside the log. It can be brought inside to make that 3 squared. In the same way, you've got the 2 there, it can be brought inside to make that 6 on 5 squared. Let's see how that works. There it is, they've both been brought inside. Now, I should mention to you, before we simplify, we always need to make sure that there's no numbers in front of the logs. Or another way of putting it is, the coefficient in front of the log must be equal to 1 for this to work. Okay, now what do? We simplify this a little bit. 3 squared is equal to 9, so it becomes 9 there. Remember, one of our laws is if we've got a plus sign between the logs, we multiply these two numbers together. So that's 9 times 16. Now, when there's a minus sign, we divide by this. So we divide by 6 squared, 36, over 5 squared, 25. Now, it's a matter of simplifying this as much as we possibly can. We do this and we get log 10 of 100, and that is equal to, well, remember our plug law? We can write 100 as being 10 squared. Now we can bring the 2 to the front, and then that's going to make it equal to 2 times log 1010, but wait, there's more, because log 1010 is equal to 1, so our final answer is equal to 2. You may remember on some previous slides we had questions just like that, and that is what you're meant to do with such questions. Okay, let's have a look at some more examples. So we've got to try and solve for x. We've got to find out what value of x makes these true statements. Well, in the first one, we can use our SOC rule. We can make that 5 to the power 3 is equal to x. 5 to the power 3 is 125, and that's it. X is equal to 125. In the second one, we can also use our SOC rule, so we can say 5 to the power 2 is equal to 2x plus 1. That means 2x plus 1 is equal to 25, 2x is equal to 24, x is equal to 12. Easy peasy. Okay, in this one here, we notice we've got the same bases there, and and we've got a minus between these two logarithms. So we can write this as log 2x plus 1 over x minus 1 is equal to 4. So notice the 4 stays the same on this side. There are other ways of doing it, but right now we're just going to leave this as 4. But now that we've got it in that form, we can actually put this into index form. We can say that 2 to the power 4 is equal to 2x plus 1 over x minus 1. But wait, there's more, because we need to multiply. 2 to the 4 is equal to 16 times the x plus 1, which is in the denominator. We need to expand the brackets, we need to collect our like terms together, and we need to divide, and so we end up getting x is equal to 17 on 14. But surely it can't always be that easy. Let's have a look and see if there's anything which ever makes this difficult. Okay, this one we notice the bases are the same. We notice there's a plus there, so we know we can multiply the x minus 1 and the x plus 1. And that leads us to expanding that bracket to give us x squared minus 1. Now we can use our sock rule and we can say 3 to the power 1 is equal to x squared minus 1. From there, we just get x squared is equal to 4. Remember that when you take the square root of this, you need to take into account the plus or minus answer. So you get plus or minus 2. And here's the essential problem. Because if you substituted negative 2 into that one, you get negative 2 minus 1, and that's equal to negative 3. Now, log 3 of negative 3 doesn't exist. So the log of a negative number doesn't exist, so therefore this is not defined. Now, the other thing is, if we sub in positive 2, 2 minus 1 is 1, that's okay. 2 plus 1 is 3, that's okay as well. And so in that case, we need to be very careful when we look at this and say, you know what, negative 2 isn't going to work. So the only possible answer is x is equal to positive 2. And then a little note down there saying you cannot find a log of a negative number. Definitely need to remember that. Make that your 6th rule, because that's a really important one. Can't find a log of a negative number. Always remember that. Okay, let's have a quick look at the change of base formula. We already know that if a to the x is equal to y, then that can be written as x is equal to log ay. What we're going to do now is take the log of both sides. When you do that, you just write log b in front of both terms. So in front of there, we wrote log b. In front of there, we wrote log b. So log b ax equals log by. This is called taking the log of both sides. Now we can use our plug law, and we notice if there's an index there, that can be written out the front as x log b a. And from there we can divide both sides by log ba. And when we do that, we get log by over log ba is equal to x. But because x is equal to log ay, we can say log ay is equal to log by over log ba. So what actually happened? What happened was that had an a and a y there, but now we've got ourselves a base of b. You'll notice that the y was on the top part there, it's on the top part here, the a was on the bottom here, and the a is on the bottom here. So, for example, if I had, say, log 5x, and I wanted to write that another way, I could take the log of, let's say, 10 of both sides, make that log 10x over log 10 5. Now, why I'd want to do that right at the moment, I don't know, because my calculator does most of this for me, but it's certainly worth knowing about. Here we've got a couple of examples. So it says rewrite the following with base of 10. So all we do, change the base so it's a 10, and the 8 was on the top, so the a goes on the top here, 3 was on the bottom there, 3 goes on the bottom here. Can you do the next one? I hope you can, and yes, you were correct. Put the 10 in there because it's taken the base 10 log. 22 is on the top, it's on the top. 5 is on the bottom, it's on the bottom. Easy peasy. And that's it, ladies and gentlemen. So what I'd say for now is may your maths be good maths, and bye for now.